Hello everybody, Dr. Schoffes is back here. Let's see whether my voice will hold up for the last few slides in this chapter 14. Remember how at the very beginning I had pointed out to you that we are dealing with three parts in here. So we're done with IR, and we are done with mass spectrometry. So now we're looking at HDI, hydrogen deficiency index, in this segment over the next few slides. Basically, what we're doing is we're looking at the degree of unsaturation. And one way of thinking of this is how saturated or unsaturated something is has to do with the number of hydrogens. Does the compound have the maximum number of hydrogens, or are there fewer hydrogens? And that then indicates that we have a degree of unsaturation, either in the form of a double bond, a triple bond, but even if we have a cyclic component. So a cyclic structure also has 1 degree of unsaturation, but more details are ahead. So in the next slide, a couple of keywords again. So degree of unsaturation, HDI is the abbreviation for hydrogen deficiency index. So many different terminology depending on which textbook you're using. And I want you to make sure you understand the general formula. For alkanes, it is CN H2N plus 2. Now, here, alkenes and cycloalkanes, they're going to have at least 1 degree of unsaturation, and therefore the formula is now CnH2n. And molecular formula for alkynes, here we have Cn and H2n minus 2. Also, please take a look at the handouts I developed, or the pages I developed for chapter 14 for both IR and MS. But here, look at the notes. Look first, try to understand which are the key skills that you need to have to interpret these spectra. On this slide here, again, this is just to outline that we need to work with molecular formula. You need to have a good understanding of any kind of representation for organic molecules, whether it's skeletal, condensed, semi-condensed. Now, we had said that in IR, you will determine what kind of functional groups are in there. So that's very easy to tell. But with mass spectrometry, and we can combine this degree of unsaturation calculations also with IR spectra. Actually, everything can become a big puzzle where we use IR, mass spec, determining degree of unsaturation if we have a molecular formula available, but then also NMR technology. So all of these can be combined for integrated problems. But again, alkanes, saturated hydrocarbon, which means they have the maximum number of hydrogens in there. Here's your formula. You should now know the other 2 formulae for alkenes and cyclohexanes, and then for alkynes. So please fill that in. Again, you can always pause to think or write some additional notes, or maybe to look up something in the textbook. Okay, degree of unsaturation. As soon as we have a pi bond, if we have 1, we get an alkene. If we have 2, we get an alkyne. Or if we have 1 or more rings. Okay, so please be aware of this. We see this easily, only single bonds. Here we have 1 double bond, so now this has gone down by 2, divided by 2, that's 1 degree of unsaturation. From here to here, we're now going down 4, divided by 2, meaning 2 degrees of unsaturation. Makes sense because we have 2 pi bonds in a triple bond. Okay, so of all of these, only the one on the left is saturated, which means unsaturation is present whenever we have a multiple bond. Okay, so that's an important correlation. We can easily tell how many degrees of unsaturation we have if we know a structure, right? So that can help us. For example, if we were to take benzene, well, I can see there are 3 pi bonds, so that's 3, but don't forget that this is cyclic, so +1 equals an aromatic ring has 4 degrees of unsaturation. So if you have a high degree of unsaturation and at least 6 carbons, be suspicious because you might have a benzene ring. Okay, so here on the slide, there are a number of different isomers shown, and you should be able to confirm that all of them have 4 carbons and 6 hydrogens. Remember, we need to be very, very good with these skeletal drawings or line angle drawings. As you can see, here we have 2 double bonds, 1 triple bond, 2 cyclic components, 1 cycle, 1 double bond, 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 right? So 1 degree of unsaturation is 1 unit on the hydrogen deficiency index. And those are the important correlations. So make sure you understand what these symbols for structures mean, that you can find all your atoms in there and how to interconvert structure with molecular formula, or to assess molecular formula and then how many degrees of unsaturations are possible. Okay, so here something else to point out. Depending on the types of atoms we have present, this hydrogen deficiency index has to take into consideration how the bonding patterns are changed depending on the atoms present. You can see that when we have a halide, this chloride, and compare it to ethane, basically the halide substituted 1 hydrogen in the molecular formula. And when we have a molecular formula and we want to figure out the degree of unsaturation, we always need to compare it to how many carbons and how many hydrogens. This is the molecular formula we have to compare to the alkane formula, CnH2n plus 2. So we're going to have different numbers here. I can just put X and Y, but that is going to then tell us how that differs from the CnH2n. Sorry, this is not, I'm not sure why my pen here has so much trouble, but this should be your CnH2n plus 2, okay? Now, how about the bonding pattern with an alcohol? So now, we really haven't changed the overall number of hydrogen atoms because we have 1, 2, 3, 4, 5, 6, and we have 1, 2, 3, 4, 5, 6, right? So all we're doing is we're inserting an oxygen. So if our original formula has an oxygen, we simply ignore it because it does not affect the overall hydrogen count. However, there is something known as the nitrogen rule. But basically what we are seeing with a nitrogen, if we have our alkane, if we introduce a nitrogen, we actually have to add a hydrogen, right? So in this case we have 1, 2, 3, 4, 5, 6, 7. Here we have 6, right? So there's an extra hydrogen in here. Now some students prefer to utilize this formula. I don't like memorizing. I don't usually use this formula, but you may use it if it helps you. Hydrogen deficiency index is half the number of, and then you have to plug in for carbons, nitrogens, hydrogens, and halides, and make sure that that figures out. But in terms of bonding structure, I always like to think about, if we have halogens, I get rid of the halogen and just replace with a hydrogen. And then I have the formula I need to compare. Oxygens we can ignore, and with nitrogen we need to subtract 1 hydrogen for each nitrogen. And I have a detailed calculation in the handout that's also uploaded onto e-learning to discuss this HDI. Okay, so this is introduced because it's very, very helpful. I've also here reiterated the page number, and you also have skill builder on page 640. Calculating this can be very helpful. If we have a 0, it cannot have a ring or a double bond or a triple bond. Okay, so you have to think differently. Here's an example. Work on this. So you need to figure out how you go from here to a formula that is just carbon and hydrogen, and then compare it to the formula of CnH2n, where you plug in for N a 5. Okay, so those are the two you're comparing, and then you can see the difference between hydrogens and divide that by 2. That gives you the hydrogen deficiency index. But again, take a look at the handout, and of course there's a lot of information in your textbook, so make sure you keep up your reading and take copious notes. We know that students who take lots of notes will do better. And that concludes this portion. So make sure you practice a lot, and I'll see you, or you can listen to me in the next video.